Hello, everybody. Thank you for joining us today. We have a really exciting session with a big turnout. I'm going to give it about 2 more minutes because people are still joining. So stay put, get some water if you need to, run to the restroom, and we'll start in at like 3:02. See you then. Okay, good morning or good afternoon, depending on where you're joining us. Welcome to our webinar today. We're going to have a really exciting session for you guys on the analysis and design of post-tension straddle concrete bends using Midas Civil. For any of you who are not familiar with our company, Midas Soft is a subsidiary company of Midas IT. We develop a total solution service for bridges, buildings, geotechnical, and mechanical engineering. Our software solution is trusted by thousands of companies around the world, and we have always strived to provide the best products and services. These are some of the product that you may be familiar with and some that you may not be. We have our bridge software, Midas Civil, which I think most of you are familiar with, and if you're not, it's okay because we will be covering it today. We also have our FEANX software, which can be used for bridges and also for geotechnical work, as well as GTSNX, which can also be used for geotechnical work. And then we have mechanical and building software as well. For anybody who is new to this platform or has not used the upgraded version, you can see some of the new features on the screen. So on the top left corner, you can see the session information. And then right next to it, you can see whoever is currently presenting and speaking. If there's any cameras active, you can see them right at the top in the center, and then the session duration can also be seen at the right. At the bottom, you'll have the most common settings buttons, so your mic, your camera, and then hopefully you don't leave soon, but your leave button is there as well. If you would like to react or get our attention in any way, you can do so using the hand raise icon at the bottom left. You can use this to either raise your hand or again, you can react to the presentation at any point. If you have any questions for us or for our presenter today, you can ask them using the chat box at the top right. And then if you have any issues or any setting questions or anything like that, you can update that using the gear button at the top right. So without further ado, I'm going to go ahead and present our speaker today. We have Amir Botros, Senior Structural Engineer at Jacobs. Engineer is an experienced structural engineer with over 18 years of experience in the field of civil engineering, with special emphasis on design and reinforced and pre-stressed concrete structures and bridges. His primary focus has been in the analysis, design, rating, and inspection of a variety of bridge types, including pre-stressed concrete girders, structural steel plate girders, concrete slab spans, multi-column concrete bents, and pile bents. Amir is proficient in commercial software packages. Additionally, he is familiar with ASCE, ASHTO, ACI, AISC, and NDS building design codes. As a senior structural engineer, Amir leads a group of young professionals on design, rehabilitation, and load rating projects. Amir obtained his master's degree in 2010 from Ain Shams University in Egypt, and he obtained his PhD from North Carolina State University. He has been a member of the Precast Pre-Stressed Concrete Institute for years and has participated in commercially PCI research projects. Furthermore, Amir is the recipient of the 2017 Martin Korn and George Nasser PCI Journal Awards, and he has also received the 2018 ASCE TY Lin Awards. So, Amir, I'm going to go ahead and give you presenter rights, and you can go ahead and share your screen when you're ready.
All right, thank you, Luciana, for the introduction, and good afternoon, everyone. So you can see my screen now?
Yes.
All right,
Perfect.
talking about the post-tension concrete straddle bends, it's one of the very interesting topics to me, and I know that it is also interesting for many structural engineers. There are too many aspects that you can talk about for regarding post-tension bends, from analysis techniques to design procedures to construction methods, and even reinforcing details can be very interesting for this type of bends. So I would just like to say that this presentation is focused more on my experience with modeling and analysis of post-tension bends using Midas Civil, like showing the tools, the advanced tools in Midas Civil that can be used to model this type of bends and run the analysis. I'll be covering particularly the analysis of you can say a case study or a particular inverted T post-tension straddle bend that we are currently designing in a project, and this project is still ongoing and in the design phase. In saying this, I would like to thank Daniel Castillo for his with Atkins Realis for all his significant contributions to this project that are still ongoing as we speak. So going into the topic, this is some views for the post-tension straddle bends. You can see those bends usually straddle over roadway or railways, and you can see the distance or the spacing from the column to the column is usually big spans. We are talking about 60 feet and larger, going all the way to 100 or 110. At least for this project that we will talk about today, the longest that I have seen so far is 110 feet. But I believe it can even go a little longer than this as well. These are examples of bends on two columns. Also, post-tension bends can be this cantilever shape as well. We call them C-shaped bends or eccentric bends. And this is also one other shape of those bends as well. Usually these types of bends, you can see them or face them in multiple occasions in projects. Whenever you have a bridge under design that crosses over a railroad or crosses over roadway, you can end up with a situation like this when you have multiple locations where the substructure of the bridge conflicts with the roadway or the railway underneath it, and you end up doing multiple straddle bends to make sure that the bridge still, you can still place your columns around the road and respect all the clearance requirements from ASHTO guides and codes, and from the railroad authority as well. So that's where you are likely to see this type of construction or those post-tension straddle bends. So we can say When to use those bends is generally when your span from column to column goes or starts on 60 feet and longer. And the longest I've seen in this project is 110, but I believe this is not the maximum that those bends can go up to. They are usually used to straddle the underlying roadway or railway, and this is mainly meant to accommodate the horizontal clearance requirements for railroad. And even if there are prospected future tracks, which is the case in many projects, you also want to make sure that even the future tracks are respected and the clearance is satisfied for those tracks as well. I would say generally when the span of the bend reaches 60 feet, it becomes more efficient to explore this option, the post-tensioned option, for a more efficient design and performance over the traditional reinforced concrete bends. So for example, in this project, one of the bends was spanning 73 feet from column to column, and we had a limitation on the depth. It had to be 6 feet just to be able to satisfy the vertical clearance requirement for the underlying rail track for this bend. So if you go and start designing this bend with a reinforced concrete option, that's what you are likely to end with. You are likely to end with stacking multiple layers of reinforcement at the bottom of the bend just to meet the flexural strength requirements. And not only this, you can even look at the practicality of stacking these bars and ending up with a clear spacing from bar to bar that is not even satisfying the code, or even if satisfying the requirement of the code, it's not practical to basically cast the bent with all this congested reinforcement in it, and basically risk having honeycombs or deterioration in the concrete because of the congested reinforcement. That's why it's usually good to explore this post-tensioned option and see how you can make your design more efficient instead of ending up with a situation like this. I would say for the methods of construction of those post-tension straddle bends, generally there are two methods, or that's generally what's commonly used here for those bends. So either the bend is cast and post-tensioned while hanging on the columns, which means that you need to have a false work to support the formwork of the bend. And this false work can be, usually it's a steel structure that's supported on shoring towers. And you have your formwork built on top of it, basically, and cast your bend. So that's what we call casting it while hanging on the columns. The advantages of this procedure that there is no really limitation for the span or the weight of the bend that you are dealing with. So it gives you more option to go to longer spans and heavier bends if you are casting it this way. Can be used also for the construction sites where it's really critical to mobilize cranes or have cranes moving around to lift the bends or put them on the columns, such that, for example, those ones with the railroads, sometimes they do not permit having movable cranes operating around the tracks during construction of the bridge. I would say also this method of construction works for both either having a bearing connection or a monolithic connection for the column bend juncture. So that provides a big advantage for those straddle bends to be able to design it either way with a bearing connection or a monolithic connection. The main disadvantage of casting the beam on the columns using the false work and the formwork is mainly you want to make sure that you respect the vertical clearance requirements for the underlying roadway or rail tracks, and also the costs that can be associated with the false work and the shoring towers. Sometimes it's getting very expensive to get a false work and shoring towers, and especially when you go on a project on a bridge and you only have 2 or 3 bends that are straddle bends in a very long bridge. So it becomes very expensive to mobilize these heavy structures to the field or to build the false work and shoring for sake of 1 or 2 bends. This is just showing an example of this type of construction where you have the false work set here on crossing or straddling the roadway, and you have the shoring towers, the steel shoring towers here, and this is supporting the formwork where you're going to cast your bent and post tension it in the air basically here. So that's the type of construction that's using the false work. The other method can be if the bent can be casted and post tensioned on the ground, and this is also one of the good methods to basically build those types of bends. And of course, when I say post-tension, can be partially or fully. It depends on the design and how many tendons can be posted, can be actually tensioned when the bent is only seeing its self-weight. Sometimes it's very difficult, or most of the times it's very difficult to fully tension all the tendons in the bent while on the ground. This can end up with stresses that are quite high in the transfer stage and crack the member at the top. So it's not really the good way to do it. But the idea is to cast it and post tensioned on the ground and basically mobilize cranes or have cranes that can lift the bent and erect it on the columns directly. And this is very similar to the steel straddle bent construction that happens the same way. The advantages of this method is basically that you can still cast and post tension on the ground, so there's no false work or shoring towers that are required, which makes it way better and easier and quicker, faster sometimes to get the bridge constructed. And you have a better control on the casting process and the post tensioning process because you are doing it on the ground as well. The disadvantages, I would say, that you have certain limitations on the what could be the length and the weight of this bent that basically can be casted on the ground, either in a plant and transported to the site, or even casted on site right away. And you still need to limit the length and the weight to whatever cranes you have that can lift this beam later or this straddle bent later and place it on the columns. So I would say this can be used for bends with relatively shorter lengths. And also the biggest disadvantage is the mobilizing of the cranes to the construction site, which is sometimes critical to the site, like sometimes operating cranes around rail tracks that are in operation is not preferred by the railroad authority, or sometimes it is difficult to mobilize the cranes to the site. And the third thing is that you need, of course, to have special attention to the process of lifting and placement in the site during this lifting and placement process, and make sure that everything is safe in the site as well. And even the girder or the straddle bent has to be checked during the lifting and the placement operations for any stresses that are induced during this process. This is an example of a bent, but unfortunately I didn't find a photo for a concrete bent, a post-tensioned concrete bent, but that's the same idea. It's similar to the steel straddle bent when you have it manufactured in shop and then arrives to the site, and basically you have cranes like this that lift the bent from the two ends and place it on the columns. That's why this procedure can be limited to certain lengths and weights for the members. You cannot cast the very long ones and heavy ones using one crane. You can end up sometimes mobilizing two cranes, which becomes more tricky and difficult. So that's one of the limitations for this procedure. The other aspects that you need to consider when designing post-tension bends away from the construction method are basically the type of connection that you are using between the bent and the column. So either using a monolithic connection or a bearing connection. There are several factors that play a role in selecting this connection type, including the span length, the loading, and the construction procedure as well. So for certain span lengths, you may be able to achieve a monolithic connection, and all the internal forces are being transferred from the cap to the column safely with reasonable reinforcement, embedment, and connection details. At some span lengths, it becomes very difficult to still keep the monolithic connection, and you want to move to a bearing connection just to release some of the forces in this connection between the cap and the column. You want to have careful attention whenever you select the bent cross-section dimensions. This needs also not only to satisfy the design in terms of flexure and shear strength requirements, but you also need to accommodate the tendon size, the spacing between the tendons, what spacing you cannot, the minimum spacing that needs to be satisfied for the tendons, and the profile for the tendons. So sometimes you can end up increasing the bend dimensions just for sake of accommodating the tendon layout and the spacing requirements. Also, the dimensions for the end blocks, this is where the anchorage of those tendons goes, and there is a special attention that needs to be done here when selecting the bend dimensions to make sure that the anchors can be installed, the anchor plates, the stressing hardware, and what would be the spacing from one tendon to the other that would allow you to get the stressing hardware or jacks and stress the tendons either simultaneously or in sequence. And of course, that's what we normally do in design for any pre-stressed member, pre-tensioned or post-tensioned, that you want to make sure the stresses in the bend meets the allowable stresses at all stages, including transfer and service, and also that the bend section has a sufficient nominal capacity for flexure, shear, and torsion, and all other requirements. So moving to the bent column connection. So this is an example of a monolithic joint or monolithic connection. So this is when you cast the column and the cap all together. And this, like I mentioned before, those monolithic connections require you to have a rigid connection between the column and the bend. So you want to make sure that you extend the column reinforcement inside the bend sufficiently to be fully developed. And this can be challenging in many ways, especially that those columns are usually close to the end anchorage zone, where you have additional reinforcement that's required here in the bend to meet the bursting, the vertical and the horizontal bursting requirements. So sometimes it becomes very difficult to extend those bars and stirrups inside the cap in this region to maintain strong connection and rigid connection. Also, the biggest concern with those monolithic connections when you understand the effects from the post-tensioning, because usually you cast the bend first and then you start post-tensioning the tendons while already the connection between the column and the bend has been established. So you want to make sure that what kind of effects or stresses are coming from post-tensioning, as well as creep and shrinkage, and how are those forces transferred into the columns and the foundation and affecting the foundation. So those are kind of the challenges that are sometimes associated with the monolithic joints. There are some situations where a monolithic joint is kind of mandatory, I want to say. So for example, when you have hammerheads or you have the C-shaped bends, cantilever bends like these, there is no other way you can have a bearing here. So that has to be a monolithic connection, of course. And sometimes we end up even doing pre-stressing for the column as well with the cap, just to make sure that we maintain a rigid and strong connection here between the cap and the column that is sufficient to transfer the forces safely from this cap to the column. Moving to the bearing connections, there are plenty of different ways that you can have a bearing connection between the straddle bend and the columns. This is just one example of it, and we call it the anchored bearing connection. So if you look here, the straddle bend is sitting on two bearings here on the columns. That's the in-plane view of the bend. And if you look at in the out-plane view, this, of course, those bends are typically very wide members. So it is more practical, of course, to have two bearings here to support this member rather than having one bearing and run into rotations and stability issues. And in addition to this, you have to think about how the load transfer mechanism happens from the cap to the column. So if you think about the in-plane condition, the cap is able to carry the loads and rotate here around the bearings and provide full rotation, and there is no restraint or moment that can be transferred from the cap to the column. However, in the out-of-plane location, all the torsional effects that this cap is seeing and the out of plane forces needs to be transferred through this bearing system with the anchors to the column. And that's basically can be achieved by, you can say, the torque or the torsion on the cap here can be resolved into a couple of forces, tension and compression, that can be carried by those anchors and transferred to form an out of plane bending moment on the column. So this is some sort of a way that you can transfer or transform the torsional moment on the cap into forces, and those forces are being transferred to the column again to make the out of plane bending on the column. So those bearings primarily needs to be designed for the unbalanced loading condition. If you have it from dead loads or live loads. What I mean by dead loads, when you have unequal span lengths on either side of the bend, like two spans that are not equal on either side of the bend, this creates an unbalanced loading condition and torsion on the cap. And of course, the live load will usually create torsional effects on the cap either way. So you want to make sure that those bearings are basically designed to match or to meet this unbalanced loading condition. So if we think about the load transfer here and look at the end of the cap at the column here, so we have torsional effect or torsional moment that's acting on the cap, primarily coming from live loads on unequal spans also can in this case, the dead load can also generate or contribute to the torsional moment on the cap as well. And we have the vertical shear or the vertical loading here at the end, and we have lateral loads that are directly up, coming from braking forces, wind loads, all types of lateral loads on this cap. So just in a simplified way, we can say the vertical loads are basically putting compression on the two bearings here. The torsional moment is kind of resolved into couple of forces, couple of equal forces with based on the lever arm that's from center to center of bearing here. Those forces are compression on one side, tension on the other side. And then if you sum up the forces here, you end up with the situation that you have two unequal compression loads on those two bearings, which is a good situation that you don't see tension on one of the bearings. You still have two unequal compression loads. And this was the case for the bends that we'll be talking about shortly in this project. All the service loading combinations yielded or resulted in a situation like this, having two unequal compression loads, which is great not to have any tension loads in service conditions at least. But even if you end up with a situation, extreme torsion situation from live load or dead load or out of plane loads, that can end up transforming one of those forces into a tension force, then you want to make sure that you have anchors as well that are connecting the cap to the column and designed for this tension load. Finally, there are some states that adopt this type of connection, which is what we call the concrete hinge connection. And this connection, you can see the cap is sitting on the columns here. If you look at the column has a shear key that is coming out basically from the column here, and we do have spiral reinforcement that extend inside the column and also extend into the cap. So this type of connection, if you look in plane, this still allows the rotation to happen, especially that we have bearing pads here that can allow this bend to rotate to some extent. So it does not provide fixity in this direction. It's kind of a partially fixed member, if you want to call it this way. And if you look at it out of plane, you have the shear key here that's protruding from the column into the cap, and this is meant to resist or to transfer all lateral loads from the cap to the column. And you have those two spiral reinforcement scheme that basically transfers any torsional moment on the cap into a couple of forces, the same idea that we had with the bearings, with the anchored bearings, but here is done with the spiral reinforcement and still capable of transferring the torsion from the cap to the column. So that's what we call a concrete hinge connection. This connection is sometimes preferred by some states to avoid having bearings under the cap, and those bearings in the future, of course, subject to maintenance and replacement. So this is one easy way to avoid having the bearings. This is actually the concrete hinge. Those caps are actually in this state, and they do have, or they are executed this way, having the concrete hinge detail. And you can see the detail is kind of clean here. You don't see the bearings. You just see as if the cap is monolithic with the column. So to recap the beam column connection thing, we want to just take some takeaways from this, that mainly the span length and the bent construction procedure are key factors when determining the connection type between the cap and the column. Also, the site conditions play a role into this. If the site condition does not allow using false work or towers or shoring towers because of railroad that's in operation or roadway or any safety considerations, then in this situation, casting the bent in air or on the columns becomes very difficult in case if you want to have a monolithic connection, and therefore the bearing connection remains a feasible alternative in this situation. We also want to say that the load transfer from the bent to the column remains a very important thing that needs to be examined carefully and when deciding the type of connection. So whenever you are planning to use a bearing connection, you want to make sure that you have a clear load path for the torsion to be transformed into forces, and the forces are basically transformed into the out of plane bending moment on the column. If this is not achieved, stay away from the bearing connections, I would say, and keep with the monolithic connection, which is going to work definitely in all situations. The effects from creep and shrinkage on the columns and the foundations is one big key factor here whenever you, especially when you use the monolithic connection between the cap and the column. as compared to the bearing connection. So in all situations, creep and shrinkage will put effects. Either you have a monolithic or a bearing connection, but one of them is kind of magnified in this scheme more than the other scheme. And there are situations, like I said before, that monolithic connections are kind of mandatory, like whenever you have hammerheads or C-shaped eccentric bends for stability. So jumping to the case study that we are discussing today, this is the plan view for the bridge, and this bridge is crossing over rail tracks. You can see clearly here we have two existing tracks and we also have future tracks, and basically you need to respect the horizontal clearance requirement from the railroad owner, and this can come up to sometimes to 26 feet or 27 feet from the center of the future track. You are not allowed to put or have any structure within this area here or area here. So this means that the very beginning location or the very nearest location that you can have a column in is going to be here and here. So you end up with the situation that you need to span 105 feet from center to center of a column. So that's when post-tension straddle bends come into play. There is no way that you can achieve this with a reinforced concrete structure. And this particular bridge had this crossing situation happening, of course, in those two adjacent bends. Then later on, the bends we were able to fit the bends away from the tracks and resort back to the multi-column bends or the reinforced concrete bends. Also, if you look at the profile view, for this reason, you need to respect the requirement for the vertical clearance measured from top of the rail all the way to the soffit of the bend. You want to make sure that you satisfy the 23.5 feet of vertical clearance or higher. So sometimes you can end up or resort to an inverted T-section kind of thing to save on the depth of the bend and be able to construct the bend and achieve this clearance. So this even specify that this bend needs to be an inverted T bend that's straddling 105 feet from column to column. That's the situation that we are dealing with here. Those are the two spans that are carried on the bend or adjacent to the bend from one side and the other side, and you can see the geometry and the skew geometry from crossing the rails ended up with two spans that are, of course, not equal. This is 130 feet, this is 84 feet. There is a big difference in the span length between the two spans, which generates an unbalanced loading condition from dead loads even on the bend. So this bend is going to be seeing torsional effects from dead loads in addition to the normal torsional effects that we see from live loads. So designing this bend, you want to come up with some preliminary dimensions. Of course, that's based on multiple factors, including the previous experience with designing the bends, how much the depth would be, and the breadth or the stem width, and the breadth of the section or the width of the section at the bottom as well. This basically came from previous experience, came from the site constraints mainly. So what depths you can use here in the bend and you still maintain sufficient clearance, vertical clearance for the rail. And even not only sufficient vertical clearance for the rail, you want also to make sure if you end up putting false work and form work and casting this bend that you still have enough overhead that you can put this member or this false work member underneath the bend section and cast it while not affecting the vertical clearance for the rails, which is very challenging. A quick way to kind of estimate the tendons is basically estimating the ultimate moment on this bend from all dead loads, factor dead loads, and live loads. And simply you can just take this moment and divide it by a lever arm from the centroid of the tendons to location of the compression force here. At ultimate, you can even estimate this lever arm like 80% of the D from the section from the centroid all the way to the top, and come up with the ultimate tension force and divide it by some FPS value, estimated value for the stress in the tendons at the ultimate stage, and come up with the area of the tendons that's required. Then you can decide on the size of the tendon, like 19 strands or 20 strands or 27 strands or whatever, and you can decide what area of the tendon is going to be and the total area that is required, and this is how you can come up with the number of tendons that you need to apply in this bend. And then you can work out your way for the profile of the tendons. Usually the post-tension members prefer using parabolic profiles or curved profiles. And there are some states that still like to use the draped profile, similar to what we do in pretension members. But at the end of the day, it's the same idea, the same effect, that you want to have the maximum utilization of the tendons right at mid-span, where you have the maximum moment. And this, of course, starts to drape upwards, where your movement fades away from the mid-span, going to the ends of the member. And of course, for this bend, we decided to use this scheme of having the bearings with the anchors, even though all the loading combinations ended up with unequal compression forces on the two bearings, but we still wanted to have anchors for any unforeseen loading effect that can result in any tension force on one side. Of course, the bearings never carry tension forces, so you want to make sure that you have anchors that, in this situation, that are still capable of transferring the load to the columns and safely to the foundations. This is to give you an idea about the tendon profile. So we have 9 tendons that were selected for this bend, and we ended up with this size, 27 strands that are 0.6-inch strands. And we ended up fitting 3 tendons per row, which is nicely done based on the spacing requirements from the manufacturer of the pre-stressing or the supplier of the pre-stressing. And you can see here the best way to work the layout for the profile, the profile for the tendons, is to basically move the tendons in the vertical direction only, and avoid moving laterally, both horizontally and laterally, as much as you can. And the reason I'm saying this, because those bends, you end up with a huge amount of steel and reinforcement and inner legs and stirrups. So you want to make sure whenever the profile of the tendons does not really conflict with the stirrup legs or the reinforcing bars that are inside the stem. So for this one, for example, we had those 3 tendons, 1 through 3 at the bottom, just moved vertically, pushed vertically downwards to make their way to the final position here at mid-span. You can see here tendons 4 and 6 are the only 2 tendons that we picked to move them horizontally, both laterally and vertically, until they make their way to the second row. And then finally 7 and 9 are only pushed vertically in the same location, and 8 was pushed vertically to make its way to the third row. And this even gives us an advantage. Even if we need to add tendons, additional tendons in the design process, we can always add additional rows here, and we still fill in the row mid-span. It's important also to keep this design in conjunction with what the supplier is providing, the post-tension supplier. So you need to revise always what the inner diameter and the outer diameter of the sheathing. Usually the sheathing is a metal corrugated duct sheathing kind of thing, and this provides good friction. And basically, when you grout those tendons later to fill in the void between the sheathing and the duct, you want to make sure that you have something that can provide a strong bond between the sheathing and the duct. So you want to revise for this size of tendons what is the inner diameter, the outer diameter for those sheathings, and also what is the requirement for the minimum center to center distance between those tendons. That's, for example, for this particular tendon size is 7.8 inches. You want to make sure that you satisfy this. Some codes call for 1.5 the diameter of the tendon, some calls for twice the diameter of the tendon, but just be aware with the supplier specs and what needs to be done, because all those spacings and requirements also dictate the spacing between the tendons here in those sections. And basically, when you decide how many tendons to use and how you can move the tendons inside the section, all of this is based on the supplier specs as well. Also, it's very important to revise the anchorage zone area, like what is the actual dimensions of the anchorages, the diameters, the inner and outer diameters, and basically make sure that whenever you get to the end block, whatever spacing you are deciding between from center to center of the anchor plates is sufficient to get the jacks to fit in and jack those tendons as well. So just to summarize for this bend, the situation is that we have a bend that is totally 124 feet long. It's 11 feet deep, 5.5 wide on the stem. So it's a big, huge section that is quite heavy to be casted on the ground and lifted by cranes. In addition to this, the site puts additional constraints on us on lifting and operating cranes in the site to lift this bend and place it on the columns. So the design team has decided to find another way of casting this bent instead of casting it on the ground and lifting it, since this is not feasible to happen, that we can still use false work and form work and basically cast it on in the air or on the columns, and then later on remove the false work and the form work and end up with a bent sitting on the two columns. The only challenge with this is to make sure that you have enough vertical clearance from the lower chord of the whatever false work that you are using. We were thinking of using baling trusses here, and basically we want to make sure that from the lower chord of the truss members until the top of the rail is still satisfying the vertical clearance requirement, so it does not affect the operation of the rail during construction. So this is kind of a quick schematic of what we are talking about. We're thinking of basically having two trusses that can run from one end to the other. And the reason for this is that we cannot have any interior shores or towers here in the middle for the rails or the tracks underneath this bent. So we want to have shores at the two ends, run two trusses from one end to the other, have some transverse members here, and basically put rubber bearings on top of those transverse members. And then we can basically build the steel formwork for this bent on top of that. So this formwork is basically going to be sitting on those rubber bearings and still supported at the two ends here with some sort of rigid support. This support also was thought about to be some sort of a series of jacks or jacking system, like what we call a height adjustable support, or jack, or a series of jacks that can be placed in here and in here, so we can adjust the height of the formwork. And the reason for basically going this route is that we want to make sure that we can raise the form a little bit until we make sure it's not, the form is not sitting on the final bearings or the anchors here on the concrete columns here during the casting of the bent. So we want to make sure that the form is not touching those bearings or not applying any load to the columns through jacking those jacks up at the two ends. And of course, we can shim those rubber bearings or add additional rubber bearing thicknesses here until we make sure the form is still sitting on the bearings and at the jacks at the two ends. Then the idea was to cast the concrete here in the form, so we can cast the inverted T section. Then when the concrete reaches the strength required for post-tensioning, we can start to post-tension partially or portion of the tendons. And after the post-tensioning, this inverted T is expected to camber upwards, so it's no longer going to be touching the rubber bearings in the middle, but it's going to be sitting only on the jacking system here at the two ends. And then basically we are going to lower the jacks at some point until the beam, of course, take off the formwork. I'm just lost here in this part. So after building the formwork and casting the concrete, the inverted T section here, when the concrete reaches the strength that's required for post-tensioning, we can take off the formwork and then post-tension partially the tendons from one end to the other. After applying the post-tensioning, the bent is expected to camber upwards, so it's no longer going to be sitting on the bearings, it's only sitting on the two ends with the jacks. And then the jacks can be lowered down to get the beam to sit on the final columns with the anchors and the bearings. And at this point, you can start removing the false work safely, the trusses and the shoring towers, and you have your bent sitting or running from one column to the other in the final stage. So I'm going to jump to the Midas model really quickly. So that's a 3D finite element model that we built with Midas Civil to basically analyze this bent. And you can see all the spans, or the two spans, are entirely modeled here using beam elements for the bulb T girders on the two sides, and of course beam elements for the post-tension bends here. And on this bent, we used plate elements for the pile caps and frame elements for the piles. This is just a zoom in, or you can see a close up of this connection here, just to show you how this bulb T girder is connected to the post tension bend. So we have a complicated system here. So because the insertion point of the bulb T is assumed to be at the top center of the girder here, so we do have a rigid link that represents the depth of the bulb T, takes you all the way down to here. Then we have a bearing that's a general spring or an elastic link that's basically defined in here to represent the bearing. And then we have another rigid link that basically connects the bearing to the inverted T section. The inverted T section was assumed to have the insertion point at the bottom center here. So this represents the depth of the ledge. And then we have another rigid link that connects those nodes to the bent. So this way we have a connection developed between the bulb T and the post-tension bent. Also for clarity, we still model the deck here using plate elements. And of course, to start a model like this, the easiest way whenever you have complicated geometries like these is to model the entire thing using DXF and importing it in Midas. Of course, running into the material definitions, we had 6 material definitions here. All of them were concrete for the different elements of the bridge of different grades. The post-tension bends were assumed to have 7 KSI. And of course, we have the steel material defined for the tendons as well. And we still needed to define a dummy concrete material. That's a material that's identical to the 4KSI deck material, but it has no weight. And I'm going to talk about the purpose of this dummy material shortly. An important thing to consider, the creep and shrinkage effects. So you want to make sure that this 7 KSI concrete that's used for the bends have associated creep and shrinkage properties to it. So this is defined in according to ASH2 here with the humidity and the volume to surface ratio and what the age that we expect the shrinkage to happen at. And of course, the concrete strength, the final concrete strength for the bend. And you can always display the creep relation with time and shrinkage relation with time, how the creep and shrinkage coefficients vary with time. Of course, for the section definitions, we did define all the sections required for this model with the module or the tools that are provided here in Midas. And you see they have nice tools that can define all different types of sections, including steel, concrete, pre-stressed. For the inverted T section, we use the section property calculator tool, which allows you to define any arbitrary section of any shape, and you can just using coordinates and nodes and calculate the properties for the section. For the tendon definition, you need to basically go on the post-tension bends, number the elements from 1 all the way. We have 61 elements on this bend, and basically define the tendon properties, the profile along the bend with the coordinates x, y, and z. So we have 3D coordinates for the tendons, x running along the bend, y is the lateral component, and z is the vertical eccentricity or the vertical direction component. So this means the strand drapes from 28 to 10. This is measured from the bottom of the inverted T to the centroid of the tendon. It's important also to note that we don't have a transfer length in this case. These are dealing with post-tensioning. And of course, we have this window that shows all the definitions for the post-tension tendon. And of course, don't forget about the method for the losses that you will be using for the tendons. So for this project, we use the approximate method that's based on the manual of the state and defining all the load cases that you have in the model from self-weight, all the haunch load, deck load, barrier load, wearing course, braking forces, post-tension cases, even all the wind load cases. This is just an example for a line load that's applied on the beam. But all those load cases were just defined using static load cases. And the most important thing to get into construction stages is to have group definitions. So basically all the members in the model needs to be defined into groups. So we have groups for the bulb T girders, we have groups for the column, we have a group for the piles, we have a group for the deck elements, and so on and so forth. You can also add all the substructure component elements in one group, call it substructure. We have those groups created for 3 different elements. For the elements, we have groups for the supports. Whenever you have any support condition like fixation, rigid links, bearings defined, you want to put all those bearings in one group, all the rigid links in one group, and basically designate this group with a name that you can understand and link to the model. Also the loads, all the loading cases are defined into groups as well. And the reason for creating those groups is this is how Midas understands construction stages. Whenever you define your stages, you want to activate or deactivate either an element group or a load group or a boundary group. So that's how you basically create your construction stages. We have total of 12 construction stages here, going from the substructure to the false work, casting the beam, post-tensioning first tendons, and then removing the false work, applying the bulb T girders, post-tensioning the second portion of tendons, and then applying the loads for the deck pour, stay in place, haunch deck load, and then activating the composite action for the bulb T girders. Then finally the barrier, the wearing course, and the long-term effects. So just for the construction stages, that's how the window look like. You start defining the first stage. So we call it substructure, and this is where we activate the element group that has all the substructure elements defined to it, along with the supports, the fixation, and the rigid links. So this is how it looks like. All the columns and the bends are kind of defined and activated in this group. Then going to the false work and the inverted T-cast, that's the second group. And basically we define here the inverted T-cap or activate the inverted T-cap elements. So those are the concrete elements for the cap are being activated here along with the false work support. So that's how we are basically modeling the trusses or the false work here. It's just the boundary conditions that are provided by the trusses. So we are not really modeling steel trusses here or members or jacks or anything. We are just activating the elements for the cap and activating the appropriate boundary condition for this stage. As you can see, the cap is basically resting or sitting at the two ends on rigid supports, and basically we have a series of point springs in the middle that represents the rubber bearings. Those rubber bearings are selected to be compression only springs, just to make sure that they can only provide reaction when compressed, but they cannot carry any tension reaction. And this is just showing the close up for the girder with the bearing condition. You can see here, if you zoom in, this I mean the inverted T at this stage is only sitting on the point springs in the middle, which represent the bearings, and the end or the rigid supports here, but there is no connection yet developed to the column or the bearings yet, so we don't have springs yet activated at this stage. And if you want to look at this particular stage, what's going to happen, so basically you will end up seeing some bending moment on the inverted T, even though it's casted on the formwork, but because it is sitting on rubber or compression linear springs here, which develop reactions here. So this puts a little bit of bending moment on the girder, but that's not, of course, the full effect from the self-weight. And you still see some loads that are gyri or reactions going at the two ends to the jacks as well. Then we move to the following stage after casting the cap is basically tensioning partially the tendons, like tendons 1 through 9, those 6 tendons here, and this can be done by activating this load stage of the post-tensioning, this group that has all those 6 tendons in it. And if you look at the deformation that happens at this stage, so the post-tensioning is being transferred to the bend, so it cambers upwards. And you will, if you look at the reactions provided here, it's only all the self-weight of the member is going at the two ends now, and all the interior rubber supports or bearings are not feeling any reactions. This is because they are compression-only springs. Also, this is confirmed by the bending moment here on the cap. You see the bending moment from self-weight with the full effect and the post-tensioning being transferred to the cap at this stage, and make sure that there are no secondary post-tensioning effects that are transferred here, since this is still considered a determinant girder here in this situation. Then jumping to stage 4, this is a stage when we remove all the force work, like the steel trusses and the members. So we easily deactivate all the group that has the force work support and basically activate the bend bearings. And that's how it looks like. Activating the bend bearings mainly means that we are activating the springs here that are connecting the girder to the column. So now we are in this final situation. We have the bend running from column to column with the springs to transfer the loads to the columns. Then comes the fifth stage when we activate all the bulb T74 girders on spans 5 and 6. This is simply activating the groups that have the girders and the diaphragms in it and the associated support condition with it. So that's how it looks like. We activated those girders, non-composite bulb T girders now. Then we go and basically tension the rest of the tendons. So the idea is to tension the rest of the tendons in the cap after applying some dead load on the cap. So that's why we selected to apply or to do the placement for the girders first, and then to tension the remaining tendons from 4, 5, 6, 10, and 11 to make sure that we don't end up with huge effect from the post tensioning or transfer. And in the meantime, we still have some effect or some dead load acting on the girder at this stage. Then jumping to stage 7, which is applying the stay-in-place form. This is just applied as a load only on the non-composite bulb T girders here, and similarly applying the loads from the deck as if pouring the deck the weight of the fresh concrete is also applied as linear loads or line loads on those bulk T girders. And then going to the ninth stage when we activate the composite action, and this happens by activating the deck elements, which are plate elements defined with a weightless material, and that was the reason why we defined a dummy material that is weightless. So this way, when those elements are activated at this stage, they only act as a stiffness and not as the weight. And finally, this stage, when we start to add the composite dead loads, the barrier load and the wearing course load, and both of them are added as linear line loads on the composite bulk T girders now at this stage. And finally, the last stage is called the long-term stage, when we just apply duration just to make sure that we are monitoring the creep and the time-dependent effects on the structure. And of course, the post-construction stages, we define the moving load case, and I'm sure that you are aware of the moving load definition in Midas. We have done it many times. And also all the wind load cases for strength 3 and 5 combination are defined in the model. This is just a sample showing how the wind load is applied for one of the cases. And the braking load also was applied directly to the bend, equally distributed on all the bearings, and the torque that's also associated with the braking force was applied to the bend. An important aspect before jumping to the final results are the load combinations. Make sure when you compile the loads for service, dead loads, and the wearing course, you want to make sure to include both the tendon primary and secondary effects, because you will be looking at stresses at service level, and of course the creep and the shrinkage secondary effects as well. However, for the strength load combinations, you only include the tendon secondary, you do not include the tendon primary effects. The P by E moment effect is not included in this stage. We only include the secondary effects from pre-stressing and shrinkage and creep as well, along with the construction stages from dead load and live load as well, and braking loads. And of course, everyone with the respective factor, load factor. So the analysis results, just looking at some results for the moment from live load, as well as the out of plane moment from live load. And the reason I'm showing those slides is just want to make sure that this connection that we established here using the springs between the bend and the column was able to transfer the torsion on the cap into out of plane moment on the column. And I think this is shown here clearly. That is very important to verify. It's showing, of course, the torsion, the shear effect from live load on the straddle bend and the torsional effects as well. And of course, combining the live load with all the dead loads with the factor loads to obtain the strength load combination straining actions. So the thing that we just have few slides remaining. I'm sorry for the long presentation, but I'm going to focus only on this component of the cap today, the normal stresses in the bend section, and make sure the stresses are within the allowable limits at all post-tension and service stages. Regarding all the other design aspects from shear and torsion and ledge design, I believe all of those are just code application. You apply the code equations and design your member. So the good thing about Midas is that you can monitor the stresses. You can display the stress along the post-tension bend from service at the top fiber and the bottom fiber, and you'll be able to look at the stresses at every single stage. So for example, this is the transfer stage when we transfer the post-tension, those 5 tendons at the beginning. This is the top fiber, this is the bottom fiber. You want to make sure you don't end up with huge tension on the top fiber, and of course the compression on the bottom fiber is within the allowable limits. Then going into this stage number 4, after removing the false work. So that's also to monitor how the stresses will change after removing the false work. And then after placing the bulb T74 girders, you can see more compression is now applied at the top due to the dead load, the additional dead load that is added. And you'll start to see the compression stresses on the bottom fiber are reducing, because anytime you apply loads, this puts more tension on the bottom fiber. So you are reducing the effect from the pre-stressing or the post-tensioning gradually. Then when you come again and bump additional post-tensioning force in the members, so again, this bumps the compression here on the bottom fiber, increase the compression again, and you want to make sure also you don't end up with tension again on the top fiber. Then add additional loading from the deck pour, or casting the deck on the 2 spans, of course, adds additional load, so reduces the compression on the bottom and adds more compression on the top. Then going forward, all of this is just adding loads for all different cases. So So basically adding more compression on the top fiber and reducing the compression on the bottom fiber, and hopefully not ending up with much tension on the bottom fiber. And finally, you can compile the stresses at the service limit state as well. And we still have the privilege of using the 0.8 factor here for the live load and breaking forces, for using the approximate method for the losses and the cross section properties. So you can see Midas was predicting a little bit of tension here, or something that's very minor on the bottom fiber, and on the top fiber we of course have compression as what we would expect at service. We have of course ran hand calculations right beside this, and to do this was a very tedious process, because you need to basically create a huge sheet, monitor every 1 foot length along the bend, and calculate all the section properties, the losses of the tendons in all different stages, one by one, to arrive to this summary that gives you the stresses in all different construction stages. So we did that for the entire beam up to here, and we were able to plot the stresses from the manual calculations. This is a plot showing the top fiber stresses at all different 5 construction stages, or the key construction stages that we have for the top fiber, and here for the bottom fiber as well. And we did a quick comparison here between Midas and the hand calculations, which came out really good on terms of the stresses. You can see those represent 3 stages of the post-tensioning. That's a transfer here, that's after applying all dead loads, including some creep effects, and that's basically at service 3. You can see even the stresses at service are like 1% different, 5% different at all dead loads, and it was kind of a little bit different here, off by 12% at transfer stage, but at the end of the day, the sign is the same. The difference is not that significant. On the top fiber, sometimes we had some differences here, like Midas was predicting compression a little bit, hand calculation was off and predicting tension, but the two numbers at the end of the day are very small stresses, so it doesn't really constitute a big concern here. And the last thing that I want to show is the tendon losses. That's also one big privilege by Midas, that you can also look at the tendon losses at all different stages, how they are affected, how the stress in the tendons is affected. I'm just showing here one stage after all the time-dependent losses happen, the Midas results as compared to the hand calculations. We still have some differences in the profile or in the values here on how the shape of the stresses look like, but at the end of the day, like the values are kind of comparable, pretty much comparable at the main sections and the critical sections of the bend. So of course, when you end up the design process for the bend, you end up with something that's hilarious like this, with huge amounts of steel. This is happening for the end anchorage, vertical bursting reinforcement, horizontal reinforcement. Of course, along the inverted T section, you end up with all types of steel for shear, torsion, hanger reinforcement, all added up together, stacked in here, and the edge for shear friction and flexural reinforcement. So that's very typical in these types of bends. That's why it's very critical to find the tendon profile and move out the tendons inside the section. The final recap points from this presentation, I would say that the post-tension straddle bends still provide the structural and the cost-efficient alternative as compared to the traditional reinforced concrete bends, especially when it comes to this span ranges from 65 to 110, and especially when you have limitations on the depth of the bend due to the underlying railroad or roadway or constraints in the site. Also, performing a construction staged analysis is considered really important, especially to include the effects from creep and shrinkage, and to be able to determine the correct and representative stresses and internal forces for the post-tension bend design. I would say there are different modeling techniques that can also impact the analysis and the load transfer. So you want to make sure what time-dependent material properties you are using, what spring types you are using, and for the load transfer, this is really important. So for example, when we use the compression-only springs for the false work, that was meant that whenever the beam you transfer the post tensioning to the beam is going to camber upwards. So you want to make sure that it's no longer touching the springs, and springs are not feeling any load in this stage. So that's why the spring type is really crucial and important. And finally, the bent to column connection type is also one of the key important factors for your design, along with the bend dimensions and the profile of the tendons are all considered key factors for an efficient design. And I'm sorry for that long presentation. I'm just trying to do my best to finish on time.
Hi, Amir. No problem.
Yes.
Thank you very much for the presentation. I think we can take a few questions, and then whatever we don't get to, I can just send to you via email. The first question I see is, did you include the stiffness of the Bailey trusses in the temporary bearing stiffness? If yes, how did you arrive at the appropriate truss stiffness? If not, why not?
So the Bailey trusses, I have not actually included the stiffness of the Bailey trusses. Just only included the stiffness for the rubber bearings that are meant to be supporting the formwork during the pour of the formwork. And because we were assuming that this bent is going to be sitting on at the two ends on some sort of jacking system or height adjustable system, and in the middle will be sitting on the rubber bearings. So I did not bother to include the stiffness for the trusses. Of course, doing this is going to be more accurate for the analysis for sure, but that is just my assumption for the design of this bent.
Okay, the next question asks, how did you quantify long-term effects in Midas?
So the idea is we are not actually quantifying the long-term effects in Midas. We are providing the time-dependent material properties, like whatever creep coefficient versus the time relationship, and the shrink and also the shrinkage coefficient versus the time. That's the material properties that we are defining inside Midas. And also we basically want to pay more attention whenever we define the durations on each one of those stages. So that is something that we need to consider, defining durations on the stages that can kind of be realistic with terms of construction, actual construction, and getting input from contractors and the design team on how long would each stage last, because this duration matters whenever the program calculates or estimates the effects from creep and shrinkage. So we are not quantifying it or inputting anything. We are just defining the appropriate material properties. We are defining the what we think are reasonable durations for each construction stage, and we just run the analysis, look at the effects from creep and shrinkage on the members, the secondary effects, of course, on the columns, on the foundations. And if it is too huge or something that we need to mitigate, we go back and revise our material properties, revise our durations. Maybe increasing duration on one stage can be better, or reducing duration on other stage. What time would the shrinkage actually start on the concrete, like assuming after 3 days, assuming after 5 days. This all matters whenever it comes to the long-term effects and internal forces in the members. So I would say that's the best guess that we can make.
Okay, and then the next question we have is, were approximate losses used within Midas in conjunction with the zero point 0.8 load factor for live load and service 3 load combination?
Yes, that's true. So the basically the those bends are whatever state that we are designing these bends for. The manual for that state requires for post-tension bends design to use the approximate method for the losses, not to use the refined method, and to use the gross section properties for the member. So if we do that, ASH2 permits us to use a 20% reduction in the live load whenever we compute the effects from service 3 load combination, which is the load combination designated for looking at the stresses on the tensile stresses on the post-tension members. So yes, we did pick the approximate method for inside Midas, and in our hand calculations as well, we did the calculations based on the approximate method.
Okay, and then the next one asks, did you club many tendons into one force in Midas Civil or did you model individual tendons? Is it easy to model the tendons?
So yeah, I mean, like we modeled individual tendons actually. So the way that we model tendons is basically define each tendon one by one, the profile for the tendon from one end to the other using coordinates X, Y, and Z, the way that I showed them in the presentation. And then we can define for each tendon what we call a tendon group. And then basically we define a load stage after that. Let's say, for example, the one that I was calling post-tension number one. So this load stage, I activate tendons, let's say 1, 3, 5, 9 in those tendons. So the way that we just define it, we define that those tendon groups are going to be active in this load stage. So whenever we activate the load stage later in the construction stage, the program understands that those 4 tendons are active in this stage.
Okay, and then the last question we'll take today is, should braking load be applied to the top of inverted T instead of bearings?
Well, that's a good question. So the way ASH2 actually requires us to apply the load for braking loads is you, of course, you calculate the load, the force, and you assume the point of application is 6 foot above the deck. So the way that this load is actually transferred from the vehicle or from the moving load all the way to the superstructure or the deck and then to the substructure is all goes back to the engineer, how he models it. So some people like to distribute the braking forces on the girders or on the deck right away and apply like a concentrated torsion or concentrated torque on the bend. Uh, that's basically calculated by multiplying the force by the lever arm measured from the point of application of the force all the way to the centroid of the bend right away. So you can apply this concentrated moment and still distribute the loads on all the girders. Or if you choose to apply the loads, lateral loads directly on the bend, the way that I've seen is most common to do it is basically simply to divide it by the bearings equally and just apply it on the bend. So I guess that's the way that I ended up doing at the end.
Okay. I think the rest of the questions I will send you via email just because we're running out of time a little bit. But
Yep.
Amir, thank you so much for this session. I know everybody really enjoyed it, and it was so great. For those asking about the PDF, um, uh, yeah, about the PDF file, I will send it um, via email after this. But besides that, Amir, thank you so much. I
You
know
are welcome.
everybody enjoyed it, so thank
Thank
you
you.
so
Thank you
much.
so
Have a
much,
great day,
Luciana.
everybody.
Good afternoon, everyone. Thank you, guys.
Bye.
Bye.